Good evening. Our presenter is Dr. Nick Arge this evening. Arge this evening. Dr. Arge is the head of the Solar Physics Laboratory, SPL, at NASA Goddard Space Flight Center. SPL is one of the largest solar physics lab in the world, consisting of 80 or so solar scientists and other staff. Prior to joining NASA, Dr. Arge worked at the University of Colorado and NOAA Space Weather Prediction Center from 1996 to 2003, and then at Air Force Research Laboratory, Space Vehicle Directorate from 2004 to 2016. Nick received his BS in physics at the University of Arizona in 1985 and master's degree in physics at the University of Minnesota in 1988 and a PhD in physics at the University of Delaware in 1997. His research interests include the physics of the corona and solar wind, especially modeling them for both basic and space weather forecasting purposes. Dr. Arge's is the lead developer of the Wang-Shally Arge WSA coronal and solar wind model, which along with the Enlil solar wind model was transitioned into operations at the National Weather Service in 2011. Dr. Arge is a member of the American Astronomical Society and American Geophysics Union. He received Denver Astronomical Society's Van Nathan Hansen Scholarship twice in the early 1980s. So in a sense, in a virtual sense, I guess, welcome back to Colorado, Nick. Please share your screen and proceed.
Okay, let's see. We usually use Teams, so let's see if I did I get it right this time?
Yes.
Okay. Well, thank you very much for that introduction, and thank you for the invitation. It's sincerely appreciated. Please interrupt me if you can't hear me or something goes wrong. One time I gave a staff meeting and I talked for 5 minutes before I realized I'd been cut off. So, wave your hands or something. But again, it's a real pleasure to be here, and also I'm really pleased to speak to the Denver Astronomical Society because I have warm or fond memories of the Denver Astronomical Society. I'm from Colorado. I was raised. I'm not going to go through everything because Mehmet covered a lot of it, but I do want to bring up a couple things. I graduated from Wheat Ridge High School in 1981, and I was a member of the DAS from the late 70s to early 80s. I still remember Jack Eastman. I was in Colorado for about 7 years after getting my PhD, so I joined for a year. And I went through some papers and I found I was actually the associate vice president of the juniors. And here's the roster from May 1980, and then here I'm listed right here. And anyway, my I guess 5 minutes claim to fame was that I made the Sky and Telescope magazine, or at least the back of my head did, back in this was Astronomy Day back in 1980 at the Aurora Mall, and I'm not even sure if that mall's there anymore. But you can see the Denver Astronomical Society banner. So anyway, the DAS really got me excited about astronomy, and and I pursued it. And what's the irony of it is back roughly in 1980, I actually gave a talk on the sun to the junior members, and 42 years later now I'm back again and talking about the sun. And I'm going to try to go and teach you what I've learned since then. Okay. All right. So anyway, we'll start from the beginning. My understanding is that you had a lecture on the sun and more from an observational standpoint. So I'll try to go through some of this quickly because maybe a lot of you know this, but just to make sure we're all on the same page. This is a little bit of a hard talk to give because it's like I know there's very new people who know nothing, and then there's people who are experts in optics or physicists, and so it's like, what's the right balance? So if I state the obvious, forgive me, and if I'm going a little bit too high, forgive me also. But the sun, is our nearest star. It's a G2 star, the main sequence star. It's about 109 Earths across, so you could fit 109 Earths across it. And its mass is over 300,000 times the mass of the Earth. And the temperature at the core, where nuclear fusion is occurring, you're converting hydrogen into helium, like most main sequence stars. And then what happens subsequently is in that process, energy, photons, neutrinos, things like that are emitted. And these particles or photons, oops, I jumped the gun here, sort of work their way out through this radiative zone, which is where photon diffusion occurs. And so, but it takes, and then it reaches the convection zone where convection, basically almost like the boiling of water, the equivalent that's the convection. And then over 100,000 years later, these photons arrive at the surface, at the visible surface called the photosphere. And by this time, the temperature has dropped from 15 million kelvins to roughly 6,000 Kelvin, and the visible surface. And the temperature, you get a little ways out, the temperature drops a little bit more. And when you get about 2,000 kilometers above the surface, then in apparent violations of the laws of thermodynamics, what happened? Oh, okay. The temperature jumps to over 1 million degrees. And that's one of the still mysteries of the sun is, how is it that the temperature jumps to, basically 3 orders of magnitude, 1,000 times the surface temperature. And I'll cover some of the things like sunspots a little bit, prominence in the solar wind and so forth. Just here again, the sun's a typical star, so primarily hydrogen, helium composition. Okay, so I was able to, this is a recent picture of the sun. These are sunspots. I'll talk about sunspots. And so sunspots, I think you probably, Jack Eastman, I think was the speaker, probably talked about observing these. But these are very strong regions. These are regions that are darker on the sun with strong, that are associated with strong magnetic fields. And that's one of the overlying themes of this talk is that a lot of what we see on the sun is, basically in its atmosphere, on its surface, and the space weather phenomenon occurs as a result of the sun's magnetic field. And so I thought the topic of the sun's a very broad, it's like you could not cover it in an hour. So I tried to narrow it down to this, and I did the best I could. Again, regions of strong magnetic fields, basically 1,500 to 2,500 Gauss. At their centers, the fields are pretty much vertical, and then as you get to their edges, they become more horizontal. Like a bar magnet, they end up having positive and negative components. They always have a leader and a follower because you can't have, as of this date, there's no such thing as magnetic monopoles. The cores here are about 2,000 Kelvin cooler. And so they're actually, if you could get rid of the rest of the sun, they're actually really bright, but they're very dim compared to the surface. So, and then small spots typically last a few days, several days, and the large ones can last weeks. And they range in size from 1,500 kilometers to 50,000 kilometers, Earth's 12,000 kilometers across. And so this is a comparison to a typical sunspot. Okay, so I think most of us know that there's a sunspot cycle. It's about an 11-year cycle, and it's been recorded for centuries. And sunspots have been known for certainly millennia. And but in hundreds of years ago, they were observed not as consistently, but they were observed. And you see there's sunspot maximum, lots of sunspots, and then a minimum and a maximum and so forth. And as time's gone by, They have become, routinely observed. And you see sometimes there's lots of sunspots, other times there's maximums weak. But there's this average 11-year cycle. Typically, it's 9 to 12 years. And David Hathaway, one of my colleagues at Marshall's Space Flight Center, he's retired recently, so he hasn't updated this plot. I was always used to updating this plot, but we finished cycle 24, and we're now roughly in 2020. We're now about 2 years into cycle 25. Okay. What does the sun's look like? What does its magnetic field look like? So this is an image of the sun's magnetic field. So this is at the photosphere. And so the dark regions here are active regions, basically where the sunspots are. This is inward directed magnetic field, so pointing into the sun. And white here is pointing outward. And so the strong field regions, in fact, let me start this movie. You can watch, and this is from the last 2 weeks. And there's like, these are applause regions. This is the decayed active region. And if you start watching this, it's just fun to watch. This guy right here is very fun. It's very active, and lots of emergence. So fluxes coming up from that, magnetic fluxes coming from beneath. But you also notice a pattern that the leader here is positive and the follower is negative. But in the south, it's negative and the follower is positive. And that's called Hale's polarity law. And so what happens over a sunspot cycle, it's positive, negative, and then the reverse. And then after 11 years, the whole thing switches and, they trade spots, and then the leaders become, in this case, would be negative. So this data, I was asked to talk about instrumentation. This is taken with the Solar Dynamic Observatory. It's a spacecraft actually led by one of the scientists in my group, Dean Pesnell. He's a project scientist. It has three instruments on it, the atmospheric imaging assembly, and I'll talk more about that in a bit, and the EVE instrument, the extreme ultraviolet variability experiment. This is for irradiance, and I'm not going to talk, there wasn't enough time to throw everything in. And then these images are taken by HMI, the helioseismic and magnetic imager. And this is taken every, several minutes, and in really extraordinary detail. Okay, so the big question is, well, you have these observations, and observations of the sun's magnetic field have been taken for almost over 100 years. So anyway, try to explain kind of in a very basic level how one measured the magnetic field. This has been done for over 100 years. Hale, George Ellery Hale, was one of the first people to do it. And it's based on what is called the Zeeman effect. And what happens is when you have gas inside a strong magnetic field and you use a spectrograph and you image the spectral lines, they're broad. Some of the lines are broadened based on the strength of the magnetic field. And so Hale, this is the 1919 paper, imaged this sunspot. And then the spectrograph, you can see the broadening of this spectral line. Okay, so this is the way it's done. And I've done this, so physicists, please forgive me, but I tried to do this at enough detail to maybe be more satisfying, but it's, you really need to use like more advanced physics to do it right. And but what happens is in a gas, you have electrons, and typically they orbit the nucleus of an atom in one direction. And if you have an observer here, it spins at a certain frequency. So it goes around at a certain frequency around the nucleus of an atom. And that gives you what is called unpolarized light. Remember, light is electromagnetic radiation, so it's electric and magnetic. Have components in it. And so an observer, so if you suddenly put this in a magnetic field and you observe along the magnetic field, what you see when the electrons go in one way, or if the field's one way, is a change in frequency, and that corresponds to a change in wavelength, in this case, a shorter wavelength. And if the electrons going the other way, or you were to change the direction of the field, it's in the other direction. And actually what it does is and the frequency is shorter, is smaller and longer wavelength. And what's going on is the electromagnetic waves have an electric component and a magnetic component. In this case, it's rotating kind of like in a circular fashion. So if it rotates like one way, right-handed way, it's called left, right circular polarization. Another way, it's called left circular polarization. The point is, and the thing you should get across is, we can use this trick to knowing that if you're in a magnetic field, you're going to see a change in wavelength of the magnetic field. And so if you get the sun and you pass it through a filter, so you only see the spectral line, or at least a small part of it, and use some components called retarders and polarizers, and even I have to review my optics for all this, but I was looking at that today. But the point is, you can isolate just the right-handed circular polarization or the left-handed circular polarization. You pass it through a grating and mirrors, and you spread out, and you get a spectrum. And what you see is, if in this right here is, if you look at, you set this so you only see the right-handed component or right-hand circular polar, you get this blue spectral line. And if you do the other direction, you get the red spectral line. And you see there's a shift. And it turns out the amount of shift is the change in wavelength is directly proportional to the magnetic field. So what it is this shift in wavelengths is exactly how you determine the field of the magnetic field. And the reality is you really need to use quantum theory, and this is only for line of sight fields, and there's vector magnetographs. The SDO instrument, HMI, actually does a very advanced, and people spend their lives doing this work. But this just a quick try to give you an idea. The shift in wavelength actually tells you something about and not only just for the sun, but they do this for stars. Okay, so now that we can measure the magnetic field, I talked about the Hale polarity law. So I won't review that other than just remind you that during one cycle, the leaders are positive filled, and the following these are active regions or sunspot regions, followers are negative. And you can see in the southern hemisphere, it's reversed. And then during the next cycle, 11 years later, it's actually reversed. North, now it's negative instead of positive. Now it's positive instead of negative. And so it's really a 22-year cycle. It's a 22-year magnetic cycle. So there's 11-year sunspot cycle, but a 22-year magnetic cycle. And I'm going to try to tell you, like, how is the sun's magnetic field, how does that happen? How is the sun's magnetic field generated? And the way it's generated is you got to understand a couple of things about the sun. One is it's a ball of gas, and it rotates faster at the equator than at the poles. In fact, it rotates 10 days slower at the poles. That's called differential rotation. But all you need to know is that it rotates faster at the equator than at the poles. There's also something known called meridional flows. Flows drag magnetic field up to the poles. Just for your information, in a plasma, an ionized gas, the conductivity is really high. And when that happens, the gas and the magnetic field go together. So if the gas goes one place, the magnetic field goes one place. So these flows drag flux up to the poles. It also turns out when these active regions emerge at the surface of the sun, over time, there's this convective boiling almost going on that causes them to diffuse. And this is called actually supergranulation, but it's diffusion. They diffuse. And the other thing that happens is when if you have one polarity run into another polarity, they cancel, the fluxes cancel. It's actually called reconnection, which I'll cover in a minute. But the bottom line is you put these two together, you get, they cancel out, and all that's left is this little residual. So I'm telling you all this because all these things come together to cause the magnetic field, the evolution of the sun's magnetic field. So if you look at the sun, and this is like a simple model of how it happens. So in the convection zone down inside the sun, if you had a magnetic field that was going just like that, what happens, remember I just told you the magnetic field gets dragged with the plasma or the gas. Well, in the convection zone, what happens is because it rotates at the equator faster than at the poles, this magnetic field line starts getting stretched out like that. Over time, it gets more and more stretched. In fact, over time, it keeps getting wrapped around and wrapped around. And this is called the omega effect. it can wrap around about once in 8 months. And after a while, it builds up and it builds up and it builds up. And as you get more and more magnetic fields pushed together like this, it's basically, there's more flux, there's more magnetic field. And it turns out that magnetic field has a pressure to it. And there's we all know about gas pressure, but there's magnetic pressure. And so if you have a magnetic pressure and some gas, and then there's just gas around it, what happens is the magnetic pressure kind of, you don't need as much gas in there to be in balance. And so what happens is there's less gas in this around in these magnetic fields than outside of it. And if there's less gas, it's less dense. And what it does is it becomes buoyant. So what happens is the gas wraps around, gets stronger, then it becomes less dense, and then it flows to the top. And that's actually what happens. That's where you get the sunspots or the active regions. These basically rise up, and because the sun's a spinning body, there's Coriolis forces that cause it to turn just like hurricanes do. And you basically get this basically inclination. And so these are active regions that we were on right here. There's a leader and a follower, and you can see that they're inclined to each other. And this is called Joy's law. It's an observational effect, but the causative of it is what I said. And so what happens is you get this plus and minus. And what happens is now they get wrapped around, they get buoyant, and they float to the surface of the sun and emerge like a serpent out of the water. And you get a positive part and a negative part. And then what happens is the meridional flows, the flows drag it upwards. And you can see what's happened is now the south pole part is going to cancel the north part. And over time, more active regions get brought up to the pole, and it eats away, this southern component eats away at the northern component until it goes to zero. Same thing happens in the south. The northern part cancels the southern part, and eventually it all gets canceled out, and the poles have reversed. Originally it was outward in the North Pole, now it's inward. That's 11 years have gone by. And then the whole thing starts over again, and the whole dynamo process, that's what it's called, dynamo process, starts over until you get back to here 22 years later. And that's what causes the sun's, that's the evolution and how the sun's magnetic field's generated. So this right here is an image of the sun's magnetic field. And what you're going to see is it's going to unwrap into a map that's 360 degrees in longitude and 90 degrees north and south. And you'll see it'll unwrap. And then you're going to watch a 22-year cycle of the sun's magnetic field evolution. So here it's unwrapping. And just notice up in the pole, this is positive, it's yellow polarity, negative polarity down here. Again, and notice that this trailing active region is positive, and this blue stuff, the negative polarity is going to flux is going to get propagated up. So it'll start here in a second. Hopefully you can see the movie. You'll notice that active regions start at higher latitude, and they'll start working towards the equator. But you see that enough fluxes come up, but now it's went from yellow to blue, and this is going to start turning yellow. We're going through approaching sunspot minimum, very few active regions. You see the polarities changed. And now active regions pop up at high latitude, and they start working their way towards the equator. And you'll see this blue get eaten away by all this flux that's going up, canceling it, and it will reverse. Now it's positive again, and now it's negative. And you can just watch the cycle happen one more time, going to sunspot minimum. And activity's picking up. Active regions are high latitude or higher latitude. And then they're going to work their way to the equator. And the polarity is going to switch now to blue or negative. And working towards sunspot minimum. So this is 22 years in time. There was a data gap in the sun's evolution. Okay, so that's how the surface magnetic, the magnetic field on the sun on the surface evolves. Okay, so let me tell you a little bit about the sun's atmosphere. And again, a constant theme throughout will be the magnetic fields, like, it's always involved in the processes. So if you look at the temperature of the suns, this is at the surface of the photosphere. That visible surface is the photosphere. This is a log scale, so 1,000 to 1,000,000 degrees, and then height in 1,000, 2,000, 3,000 kilometers. Remember, the sun's 700,000 kilometers in radius, or about 1,000,000.4 kilometers in diameter. But what you see is, right at the surface, about 6,000 kelvins. It reaches a little bit of a minimum and then increases slowly. And then at 2,000 kilometers roughly, it just suddenly, in what this is called a transition region, we pass through what is called the chromosphere. Suddenly, in a very small distance, the temperatures has increased to 1,000,000 degrees. It's increased by a factor of 1,000. Now it's up to 1,000,000 degrees. And this has kind of been an outstanding mystery. It still is a mystery in this, the field of solar physics. How does that happen? You'll see here the density also drops a lot, 8 orders of magnitude drop, 10 to the 8th difference in densities. To sort of tell you the answer to and you won't be surprised what the answer is, but when I took solar physics, I mean, we already thought it was the magnetic field, but my solar physics professor taught us. He said, well, let's see if let's say it's sound waves. Is there enough energy? It's like, no. But it turns out there's enough energy for the magnetic field to do this. And we know it's the magnetic fields. The process, I'm going to go through in a little bit more detail, but we understand it's magnetic field, but the details are still being debated. So here's back to the Solar Dynamic Observatory. Now we're going to talk about, and we just saw measurements from the HMI instrument. These, Dopplerograms, that's basically measuring the perpendicular velocity of the gas. The magnetograms, that's when you measure magnetic field, it's called a magnetogram, and then visible light. And then, so this AIA instrument looks at the sun and for everything from 1,700 angstroms down to 131 angstroms. So this is extreme ultraviolet. And basically from temperatures equivalent to 4,500 Kelvin up to 10 million Kelvin. Okay, now we're going to look at the sun around 600,000 degrees Kelvin. And this is a really interesting movie. This is the sun. And at 600,000 degrees Kelvin, and you can see all sorts of things going on. You can see it's not quiet and just boring. It's very active. Here's these active regions. Now you can see that they're, lightening up and dimming and so forth. There's all sorts of activity happening. There's these little filament things. These are magnetic fields. These are what are called flux tubes, or magnetic field with gas on them that's heated. And we'll let the movie start over, but notice in here, you'll see this, what's called a filament. This is cool gas resting on the magnetic field. And you can see it gets actually, it can become unstable. They can sit here for like weeks and then suddenly get unstable. And right here, you'll watch this right here. It's sitting there, and then suddenly it's getting unstable, and then it lifts off right there. That's a filament eruption and probably what is called a coronal mass ejection. So a bunch of gas gets sent off and having space weather effects. But you could watch this movie over and over and observe there's these little tornado-like features that occur if you watch like in here. I'll let you do that, and then I got to keep moving. But like these little tornado-like structures. And these little brightenings are little small flares. Okay, so let's look at the surface of the sun. Okay, so we're looking at the surface of the sun. This is only 1% solar diameter, 19,000 kilometers. And these are basically granules. These are basically convection cells boiling. You see it in your water when you boil it, if you're boiling eggs or whatever. They're about 1,000 kilometers across, they're traveling, they move upwards a little bit faster here than here, about a 500 Kelvin temperature difference. But these little bright regions, these are magnetic fields, and they get pushed to these boundaries. And you can see they're getting jostled and shook and changed and pushed around. And it turns out if you take a magnetic field, it's just like a string. Let's like imagine a guitar string or something. If you shake it, it sends a wave up it. And so these things actually wave, like just like like if you were to shake a rope, it sends a transverse wave up there. And that's called an alphane wave. But the bottom line is waves are going up and down these lines. And there's even other kind of fancy waves that travel up them. And they're traveling up into the sun's atmosphere because of all this agitation and so forth. And just to tell you, these are new data from the Daniel K. Inouye Solar Telescope, DKIST. This is the world's largest solar telescope. It's located on Haleakala Observatory on the island of Maui. And it's a 4-meter reflecting telescope. And anyway, this is and it's been years in the making, and it's finally taking these really cool observations. Okay, so what's going on here in the corona and the photosphere? So I told you there's this photosphere, and these are magnetic fields. They're getting jostled. And what's going on here is this is a sounding rocket data, but this image of the sun basically at 1 million degrees in extreme ultraviolet light. And these are magnetic field tubes filled with gas that are glowing. And what happens is these guys get jostled, and so the fields get jostled and twisted and shaken and so forth. And you get even sometimes interlinked and pushed together and so forth. And oops, I jumped the gun here. So they actually can get intertwined, and they can get pushed together. And if you look carefully right in here, if you take like a cut, you can see that the magnetic field's going one way this way, and the magnetic field over here is going one way the other way, and it goes through a zero. The field actually goes through a zero, and that's called a current sheet. If there's no field there, there's more gas, there's more, and their electric currents go there. These are on the scales of, we were talking about 100,000 kilometers, and this is about 1,000 kilometers. We're talking about 100 meters now. And what happens is a process, when you push magnetic fields of opposite polarity together, you get something called magnetic reconnection. Okay, so this is, to tell you the story up front, this is how magnetic field gets converted into energy, other kinds of energy. So fields of opposite polarity get brought together, gas gets pushed together, and they reconnect. And that some of that magnetic energy goes, and it's like a rubber band that gets snapped and it's like released. That magnetic energy gets converted into kinetic energy or energy of motion, and also heat. Okay, so you're now converting magnetic field into energy of motion and heat. And this is a key process occurring throughout the sun and also throughout the heliosphere. That's basically from the sun all the way out to the end of our solar system. And they get jettisoned at these high speeds called the alphane speed, but the bottom line is the gas gets jetted away, and it's heated and accelerated. And so that's what's heating the corona. These little eruptions are called nanoflares, little teeny bursts of energy that convert magnetic energy into heat and motion. And more details, you can look at my colleagues, one of my staff's papers, Nikki Vial, but they produce magnetic waves or alphane waves. And that's what's heating the corona. Now, I thought this would be really cool. This is a brand new technology. And my staff member, Adrian Dawes, working on this. It's called a photon sieve. Because why do we care about that? Well, we want to look at these little teeny 100-meter scales, right? To see what's happening. And it's like, and that's really hard to do with regular optics. So what they've done is they use diffraction. So they create, this is a wafer where they cut little slits on it of different widths. They're narrower up top and wider up here. And if you know anything about diffraction, when light goes through a thin slit, it bends. And the narrower the slit, the more it bends. So here they're really narrow. Here they're really narrow, and here they're thicker. So what happens is it bends more here and bends less near there. It acts like a lens. Okay, this distance is 40 meters. All right. And so what happens is, in fact, Adrian told me that, the surface requirements are so, this requires less, it has more relaxed surface requirements compared to conventional optics. He said you'd almost have to grind these to the size of an atom to get this kind of tolerance. They're lightweight. They're still fragile, so we're working on that. But it gives you diffraction limit resolution, meaning you can see very small scales. And in fact, there's an instrument called Visor that's going to go up. It can get to 0.1 arc seconds, or about 70 kilometers. Now that's still 100 times or 1,000 times more than we need still to get smaller. But this is a big step in technology. What's cool about this is what they do is these are two CubeSats, okay? And what happens is one of the CubeSats has the photon sieve, and the other one has the detector. And they fly, and in this particular case, they fly around and line up every now and then they can take observations. The next step in technology for this, though, is to have them fly in what's called flying formation flying, where they actually keep, we have to develop the technology so they keep aligned. And sometimes alignments have to be within fractions of a millimeter to be, that accurate. And so we're working towards that. But this is like the new thing for solar physics, to see high resolution components in the sun. All right. So now let's look at the sun's corona. That's its atmosphere, the corona. And this is just a cartoon from a book. Okay, so nothing profound here. But over here is data, just to let you know. But the sun has, the theme is it's a magnetized plasma, and it has magnetic fields that start at the surface and are closed and come back to the surface. These are called helmet streamers. These are magnetically closed regions. And you can see right here, this is an artificial eclipse of the sun. This is from a spacecraft that I'll talk about in a minute. But these are these helmet streamers, okay? And then there's regions that the sun's atmosphere is 1,000,000 degrees, and it actually drags, that's so hot, it drags the magnetic field and carries some of it out into space, into interplanetary space. And it stretches these out, and this is what we call the open magnetic field. And this is where the solar wind plasma from the sun boils off and streams out into the heliosphere. Okay, so we have closed regions and open regions. These are called coronal holes. And you don't worry about the math here. But if you watch this, this is actually data from 1997. So it's kind of dated, but just watch. If you see here, this is a coronal hole, you'll see gas streaming out. And these structures that look like they're fixed, they're actually not. They evolve. So let me see if I can get that going. You see it, they stay, and then they erupt. And those are called coronal mass ejections. And you can see the gas streaming off here, right? And you'll just let cycle through this a couple of times. But these structures are, the sun's constantly evolving and blowing off parts of its atmosphere. And we'll let this cycle through and then go through. And what I want to show you is these eruptions, they're going off to the left and right of the sun, or the east and west of the sun. Now, on May 11th, just watch, you'll see a smoke ring come out. Okay, as we do this. Okay, so you see these eruptions, and then you're going to see a smoke. See that smoke ring? That was one of those coronal mass ejections, but that's headed towards Earth. And we know when you see, like, it's called a halo CME, that is coming to Earth, and there's going to be space weather effects. And so they look for that kind of thing. Okay, so all those data that you just saw was from the SOHO Solar and Heliospheric Observatory, SOHO. And here's a spacecraft that was launched in 1995. It's still in operation. It's used for space weather operations. It's 27 years old, and we're relying on this for our space weather predictions. It's between the sun and Earth by 1.5 million kilometers, so it's about 1% the way to the sun, and it's in this halo orbit. And so it was launched, and it orbits in this halo orbit, and it's about 1.5 million kilometers ahead. And this is the instrument that, with the gas that I just showed you, is called LASCO, the Large Angular Spectrometric Coronagraph. And it's actually 3 coronagraphs together, looking inside, further out, and then even further out. And we'll show you more data from that spacecraft. This is data from a coronagraph, but this is a ground-based one. And but this just shows you how the sun's atmosphere magnetic field looks like. These are artificial eclipses. This is just we call it white light data because the photospheric light, the light from the sun surface goes up, scatters off electrons in the corona and shines. And this is basically what you see during a full eclipse. And you can see during solar minimum, the structure is like this. Turns out the magnetic fields are really strong and pushing the gas this direction. And then during solar maximum, you can see that it's very different structure. The magnetic field of the poles have basically disappeared, and these structures can appear anywhere. So the corona changes, and it's all due to the structure of the magnetic field. Coronal holes, I talked about them. They're the magnetically open regions. So right here, so there's a theoretical definition, and that's a model will show the fields open, and let me show you that. So the light and gray here is actual data, magnetic field measurements, and then a model extrapolates the magnetic field out into space. And these regions here that are open, that these are closed, these open fields are coronal holes. That's where gas can escape out into the heliosphere. If you look at decided at temperatures of about 1.5 million degrees, there's these dark regions, that's a coronal hole. And I'll show you some better examples in a minute. But these are the same.
Mr. Arge?
Yeah.
That white thing in the on the left kind of looks like my ball sack.
Anyway, then on the far right, you have a coronagraph observation, white light observation. These are all taken. This is a model these are all simultaneous. And what I did is I thought what would be interesting is let's take this and superimpose the magnetic field on there. And you can see we actually match this really well. The field matches. Now it's dark here because gas is leaving and it's less dense.
Dr.
And-
Mehmet, and so would somebody mind if we just remove that person from the chat or from
Lauren, stop fucking snitching,
I
bro.
think it's very inappropriate and they should just be removed from the meeting.
I'm trying.
Snitches get stitches.
It's one of the drawbacks of the Zoom meetings, I guess.
Yeah.
Tell me when to start. I'll try to continue on. So the thing with
Yeah,
that is,
please proceed. He has been removed.
Okay. Oh, okay. So when the magnetic fields here, they're confined, there's the density is higher, and so it's brighter. That when the gas leaves and goes out in the heliosphere, it's lighter. I mean, there's less gas, so there's less light. And that's a coronal hole. This is from ground-based observations on Mauna Loa. That's actually was a very old coronagraph. Their newest coronagraph is called the K coronagraph. And they make routine observations of the corona. So this is located on Maui, the Mauna Loa Solar Observatory. Here's coronal holes, different types. There's polar coronal holes. There's mid-latitude equatorial holes. There's coronal hole extensions. These are brand new observations, or at least newer. And if you look here, this is like an eruption that occurs. You can see when there's eruption, there's this dimming that happens. And basically what's happened, the eruptions happen and it's letting off gas and it's basically evacuating. And that's called a transient coronal hole. Okay, so let me just talk about what is the solar wind. Well, I've kind of described it already, but solar wind is hot magnetized plasma that streams from magnetically open and the sun's dynamics, so even intermittently open regions, such as coronal holes. So the coronal holes are the main source of solar wind. The speeds range from about 280 kilometers a second to about 750. And we categorize in fast wind, that's mostly faster than about 450 kilometers a second. They come from big coronal holes, like from the poles. And slow wind comes from mid-latitude coronal holes, the boundaries of coronal holes, and even from active regions. And they're usually slower than 450 kilometers a second. So the solar wind was sort of surmised back in 1951. Biermann, if you guys done common observations, there's a dust tail and there's a plasma tail. This is an ionized gas. And it was like the ionized gas part looked like it was always radially away from the sun. So long here is towards the sun, as if there's something pushing the gas radially out. And it turns out that's the solar wind. And then after that, two physicists, Chamberlain and Parker, surmised two different explanations for this, or different explanations of the same thing. Chamberlain survives what is called the solar breeze, which is about 10 km/s wind, subsonic, less than the speed of sound, blowing out. And Gene Parker proposed supersonic wind is traveling faster than the speed of sound. He did a hydrodynamic wind, fluid flow wind, and of 500 km/s. So these are very different predictions. And so he made this basically a model. And it turns out if the Earth's atmosphere is in hydrostatic equilibrium, meaning that it's static and only a little bit trickles off just because of sublimination essentially. But the bottom line is it's static. Now it turns out the sun's atmosphere is so hot that if you try to put it in hydrostatic equilibrium, if you do the calculation, the pressure of the sun's atmosphere out in interstellar space is about 100 times bigger than the pressure in interstellar space. So there's no way it can be in equilibrium. It has to flow. And so based on some of those facts, Gene Parker came up with this model. And here's basically a diagram of the solutions. So this line separates speeds less than supersonic and faster than supersonic. But what it does is starts off slow and it really threads the needle. Right here, it goes from supersonic, subsonic to supersonic and continues on. And that's the Parker solution. The Chamberlain or solar breeze solution is one of these. And so he basically explained the solar wind, and then Marcia Neugebauer in the 60s used Mariner data to make and use those data to analyze solar wind observations. She was one of the first to see it and to help explain some of the physics, and largely confirmed Parker's model.
Pause.
Now, what happened is it turned. I just told you the fastest one is 750. So there's something more to it, and of course, something more to it is this is a gas pressured model, and it turns out the magnetic field actually gives extra energy. So there's a magnetic influence. So basically the method accelerating solar wind is still a matter of debate. But it's due to
Sorry,
two ways.
Dr. Arge, can I interrupt? Dr. Mehmet, can you please remove Quanda Dingle from the meeting? They just called in on their cell phone and I can tell that they are going to interject with inappropriate content.
No, we're not.
You need to grow up. Thank you. I'm sorry about that.
Oh yeah, it's what happens, I guess, when you're young and bored. So anyway, the exact acceleration mechanism is not completely known, but we know that basically, like in the fast wind, waves are heating it, these alphane waves, and reconnection probably accelerates it in the slower regions. Now, one of the spacecraft that was launched in 1990 was called the Ulysses Spacecraft, and it was launched out to Jupiter and then went into a highly inclined orbit up to 80 degrees in latitude, and would pass over the sun's poles. And so here are observations of the sun's solar wind over its first passage and the next orbits. And this is a polar plot. So this direction is speed. So this 500 kilometers a second, 1,000 kilometers a second. So in its first orbit, it literally, the speed was observed to be about 750, like I said. The color here is the polarity, so it's outward. And it only got up to 80 degrees, so that's why there's a gap. It's not a data gap, it just never got to 90 degrees. And then right when you get to equatorial, get into the slow wind, and then again, back into this fast wind, but opposite polarity. Now this is during minimum. During maximum, when the activity was going on, it was all over the place. And then the next minimum, pretty much like this, except the poles, magnetic poles are weaker. And so this slow wind region was more expanded. And so this spacecraft ended in 2009, but it really opened the eyes on the solar wind. I do want to talk about one of the newest missions called the Parker Solar Probe. It was launched in 2018. Gene Parker, who unfortunately just passed away a month ago, was basically he's considered almost like the father of solar physics, because he explained the solar wind and many of the magnetic reconnection processes that I was showing you. He is the first person to be named, a living person to be named after a spacecraft. So he got to see a spacecraft named after himself launched.
Yo, Gene Parker looking like a monk.
and he got to see he actually got to see data from the spacecraft. This spacecraft basically measures the plasma in the heliosphere. What's unique about it is going to touch the sun's atmosphere. It was launched in 2018 in this orbit, and just follow it. This is Venus right here. It orbits and gets closer and closer to the sun. And you'll see in this next orbit right here, it'll encounter Venus, and every time it does, it gets a little bit closer. It's eventually going to get to 8.5 solar radii from the sun. If in basically basic terms, if the distance from the Earth to the sun was 100 meters, or a football field, you'd be on the 3-yard. It'll get as close as the 3-yard line, and it's going to fly through the sun's atmosphere. It's the spacecraft. I actually saw it here before it was launched. I got to see the spacecraft, and this heat shield is made out of carbon, and it's like 8 to 10 inches. And it turns out that when it gets really close to the sun, it'll be incandescent on one side, and it'll be at room temperature on the other. That's how careful, how good of an insulator it is. And they've got to keep that pointed that way so nothing melts. All right, so let me, with the time I have, let me talk a bit about solar flares and coronal mass ejections, and then I can answer, I'll say one slide about stuff I do. But we've all heard of flares, and this is the Hinode telescope. I'm not going to talk about it, but it's a Japanese telescope. But this is a solar flare, a fairly major one in 2006, and just you can watch it. Let's watch it again, and you can see that there's it's this big burst of light. You see all these like little flux tubes, these little like bright loops of gas. Okay, so let me explain how they work. Flares were first seen in 1815 by Carrington as the white light flare. White light flares seen with invisible light, are extremely rare and extremely bright. And it's no flare of this size has been observed since. And basically, ice core studies have shown that they typically last on every 100 years. They occur every 100 years, so we're overdue for a big one. And then they've been observed in the red line of hydrogen, and then X-rays in the 70s, and then X-rays in extreme ultraviolet in the 90s. I showed you some from the SDO instrument in the 2000s, and we saw also some SOHO data. But what they are sudden bursts of radiation that they come on, they switch on pretty quickly. They last minutes, but they can occur within minutes, and they last hours. They can emit basically virtually all the different wavelengths of light: hard X-rays, gamma rays, white light, soft X-rays, EUV, even in the radio. This is a key point. They emit a large quantity of energy in a small amount, in a small volume, in a short period of time. And a typical flare is 10 to the 27 ergs. What does that mean in real world terms? The bigger one, a large flare, which is 10,000 times, is equivalent to 25,100,000 megaton nuclear bombs. It's a lot of energy. They can reach temperatures of 100 million kelvins. And the only viable energy source are the intense solar magnetic fields. When I taught solar physics, I showed you there's plenty of energy to generate that much. There's plenty of magnetic field energy to generate this. This very rapid method of converting magnetic energy into particle and heat energy is through magnetic reconnection. And the thing is, we have to get gas in a very confined area, which you can, and it generates it. Here's a model of, this is the standard model of a flare.
Octavius Quandale Dingle here. That looks like my pussy.
Can you please mute yourself?
I think our visitors was back. Anyway, so what happens is this is the standard model. So you basically have magnetic field lines that are looped around like this. And remember that prominence I showed you that lifted off? Well, that's the prominence. And the magnetic fields will be sitting there. This will be resting on these fields. It's cool gas. And then because of all the turbulent motion going on and the convection and so forth, these fields can get energized and very stressed, and eventually it can get pushed together. And what we learned is when this gas gets pushed together and the fields are opposite, it'll reconnect. And this basically, it's like cutting a rubber band. This will allow this to fly off into space. It erupts the filament, erupts the gas. You get a coronal mass ejection. And then, of course, the gas particles also go back in. So what the flare part is particles coming in and hitting the surface and basically high energy particles. And then what happens, it emits X-rays, gamma rays, white light, and so forth. And if you watch that movie carefully, what happens is the field lines reconnect or reform. They reform and form little loops on the inner part, and then further out as the lines keep coming back together. Flares almost always occur in active regions. Okay, so those are flares, and then the next thing is coronal mass ejections, and this is older data, but this is one of the most active periods in the last couple of decades, and so it's really worth watching. These are what are called the Halloween storms, viewed by Soho Lasco. And so this again is an artificial eclipse. This is the size of the sun. This is the occulter. There's a little bar here holding there's a little disc there to block the light. This is a planet, probably Venus. I'm trying to remember, but watch this. You see all these gas getting jettisoned out. These are coronal mass ejections. And you'll see lots of eruptions going on. And you'll start seeing, every now and then an eruption happens, you'll start seeing like little, what looks like snow. And you see the snow? What that is those are energetic particles. See that? Those are particles, high energy particles striking the CCD of the spacecraft and the instrument. That's radiation. And if you're an astronaut or if you're an electronic piece of equipment, you do not want to be exposed to this. Okay. So this is high energy, but these are some of the strongest flares seen in recent history. They classify by X, M, and C, and X28 is really big. Fortunately, it actually was directed away from the Earth, the biggest one, so it wasn't as fancy or as impressive on here. But these are big flares. Carrington's was bigger. Okay. So coronal mass ejections are large eruptions of plasma ejected from the sun. It's not like there's more gas. It's just basically the gas is removed from the sun. They tend to have very strong magnetic fields inside them, and that can actually impact the Earth and cause lots of problems with the Earth's magnetic field. They can be ejected from speeds of near 0 to over 2,000 kilometers a second. Carrington's CME arrived at Earth in 18 hours. They typically get here in 2 or 3 days. That's how fast it was. If they plow into solar wind, they can form shocks, just like you've learned about shocks in astrophysics. Those shocks are where those particles are accelerated that created all that snow. Those strong shocks accelerate particles, and that's what you have to worry about if you're an astronaut or a spacecraft. They can create. It turned out in the Apollo missions that there was a flare big enough and a CME big enough that if it had occurred during the mission, it could have caused the astronauts to have radiation poisoning. Okay, so here's some old data, but it's really telling. Here's one of those helmet streamers. You can see it's getting energized. This is a magnetic field, and you can see right here it's starting to erupt. This is the core. It's called the filament, and you can actually see the magnetic field structure here. If we flip this diagram here over, what it is you have magnetic field loops going here. There's a filament. There's a sort of a void or a cavity. There's a plasma pileup and then a shock. And what happens is when these magnetic field lines get cut, this thing erupts. And you get a coronal mass ejections and solar energetic particles. Just to let you know that I'm not going to go through this. I'd rather answer questions, but there's multiple theories on and they probably all have some truth to them on how CMEs erupt. But basically you have to energize a magnetic field, then have reconnection so it can be released, and then buoyant forces take over after that. So space weather, I have one slide on this, but let's go through this maybe a little bit more slowly. Space weather is the conditions on the sun and the solar wind the magnetosphere, which is the magnetic envelope around the Earth, the ionosphere, the thermosphere. These are the layers of the Earth's atmosphere that can influence the performance and reliability of spaceborne and ground-based technologies. This is like, communication satellites, astronauts, the space station, etc. That can endanger human life and health. You don't want to be around. Every now and then, the astronauts on the space station need to go to a more shielded area of the space station to be prevented from getting exposed to radiation. We've talked about all these. All these have magnetic influences: coronal mass ejections, flares, solar energetic particles, and high-speed wind. Coronal mass ejections, they come in a day to 4 days. Carrington's came in 18 hours. They last a couple days. They produce geomagnetic storms, and so you'll see aurora. You can see basically impacts of power grids happening. In 1989, there was a CME that brought down the Quebec power grid for a day. All right, it can impact radio communications. It can impact navigation. It can even corrode pipelines. Okay, flares travel, that the light travels at the speed of light, so it gets here in 8 minutes. They last minutes to hours. They can increase ionosphere's density, increase neutral density. It can pump up the atmosphere. In fact, a month or two ago, Starlink had launched a series of CubeSats, and it was in low Earth orbit, and they were released them, but a coronal mass ejection and flare occurred, and it increased the density of the Earth's atmosphere, caused drag. It was 50% denser, caused drag, and they lost 40 of the 49 the CubeSats. So there's real world impacts here.
Doritos mad good.
Let's see, energetic particles. I've talked about that. It can cause
Courage or nacho cheese?
They're nacho cheese, bro.
Yes, sir. Hey.
So
Shoot, I think we're interrupting something. Sorry,
I'll
go on mute. Ah!
I'll just wait.
Oh shoot, I wasn't muted the whole time.
So energetic particles and high-speed solar wind, and so this can affect. Some of these particles can cause charging. High-speed wind can actually enhance the Earth's radiation belts, the Van Allen belts. I think if you've heard of those, some of the spacecraft and the space station will fly through these, and so you have to be careful, and so forth. So there's real-world impacts, and I can talk more about that if you want. And then lastly, just a little bit about me before I finish. And I'm the main developer of the Wang-Shaley Arge model. I actually have a team of people helping me now. It's a coronal solar wind model. It's an empirical model and physics model of the coronal solar wind. Here's the magnetic model, what it looks like. This is, I inherited this in 1996 from Yiming Wang and initially. It was a research model. They were at Naval Research Library, and I helped bring it into operations at the National Weather Service. So this model is used for coronal and solar wind studies. It supports NASA missions like the Parker Solar Probe, community research objectives and needs. It's operational at the National Weather Service. The Department of Defense uses it. The UK Met Office, Meteorological Office in England uses it, and the Korean Space Weather Agency uses it. And it's been in operations for like the last 11 years. And I just thought right here it'd be fun to show you, because I didn't talk about the Solar Orbiter spacecraft, but this is a spacecraft that basically orbits between Mercury and Venus. And this is just an example of the model's predictions at Solar Orbiter and also as viewed from Solar Orbiter. So it's saying this is where the solar wind's coming from. These are the Coronal Holes. These are data driving it, and this tells you what the solar wind speed is today, tomorrow, the next day, and where it came from. So it gives you the speed and the sign of the polarity. And this is what the magnetic field looks up higher up in the atmosphere at 5 solar radii. And it just kind of tells you whether you're in positive polarity or negative polarity. And this is all very useful for science purposes. And Orbiter needs this because they need to know where to point their telescopes days in advance. And we can tell them, point to this region or point to that region. And finally, if there's any, we do have an internship program at NASA Goddard Space Flight Center. Here's the link. But if you're a young scientist in high school, it's for high school, undergraduate, graduate, you can come as an intern for the summer or even the fall and spring semesters. You can be an intern, Pathways intern, that's pathway towards literally becoming an employee at NASA. A fellow is basically, my student started as an intern and she's now a fellow and she's got her doctorate and doing her research. And we even have international interns. And with that, I'll just say thank you and ask for questions.
Okay, well, thank you, Dr. Arge.
Very good
I
job,
really
Dr. Arge.
apologize for all these interruptions. Now, who is this person? Mike Hunt.
Stop! Dr. Ansoy, stop!
And actually, you can also email me if you have questions or you want to know about our internship program, but you're welcome to email me for follow-up. So I thought I'd add that.
Yes, we have a question from Roger.
Hi, this is Roger Clark. I have two questions. The first question is, so did you develop the Wing KP model that many of us use?
No, oh no. Actually, I know Simon Wing. We actually went to school together. But he basically no, it's a different. It's Wang and Chile. So no.
Okay. So my real question was, on a positive thing from the sun, besides it gives us warmth and everything, and some people are just idiots, but I have observed an interesting thing with not coronal mass ejections, but the coronal holes.
Right.
It seems like air glow decreases when the energy from a coronal hole is hitting the Earth. Now, I've observed this a couple of times. I don't know if it's a real effect or just a coincidence, but for observers or astrophotographers working at night, air glow is a significant sky glow problem that impacts our images. So we want to minimize air glow. It'd be nice if there was an air glow prediction. I haven't seen anything that does that, but during a coronal hole, when energy is coming to the Earth, I've observed a couple of times now significantly decreased air glow, like factors of 2 to 4 lower.
Oh, that's really interesting. I've in many cases, I would argue we're connected to coronal holes all the time. So, but maybe you're talking about maybe a big coronal hole, or if there's, if you're at the center coronal, you have a really fast one. Maybe you're saying there's some pattern there that you're seeing.
Yeah, they were big coronal holes.
Okay. So maybe
my butt was bleeding.
Yeah, I can't really explain that one. I've never heard that before, but I could certainly ask that. I don't know if that's a coincidence or if there's something to it. I don't want to poo-poo it because that you're often wrong when you do that. But I can't right now directly connect the source why that would be.
And then, is there any prediction of air glow?
There probably is, but not with what I do. We don't do any. I mean, I'm sure the Earth Sciences group at NASA has got air glow models, but or maybe the ionospheric people do, but not the solar. We're kind of solar centric, as it were.
Okay.
May I suggest, Nick, can you end the sharing of the screen?
Oh, sure, absolutely.
Okay, now that I can see everyone, we are unfortunately having this hacker problem. Please raise your hand or put your question in the chat line for our speaker. Roger, you had your question, I think.
Yes,
Any other
I just
question?
like to add, very
Yes,
great
Roger.
talk, really good.
Oh. Hopefully it was,
Okay. Any other questions, please? Gary.
Yes, if you can hear me.
Bro,
You
your
can hear
old
me.
farts are so slow you can't catch me.
Okay, anyways, high energy cosmic rays that come from outside our
mhm.
coronal, the envelope, past Voyager. Almost, Voyager went through the bubbles. So do any of those energy particles that come from the sun, can they be potentially that dangerous, like a high energy cosmic rays?
Yeah, the actually cosmic rays, yeah, do actually can cause radiation and can cause damage too. What's interesting is that is during solar maximum, when there's lots of coronal mass ejections, it turns out these coronal mass ejections have strong magnetic fields in them. And so what happens is they tend to shield, it's kind of like, you get these energetic particles from the sun in one case, but then the magnetic fields from these coronal mass ejections actually suppress the cosmic rays. And so during solar maximum, you have less cosmic rays than during solar minimum.
Yeah, so I know that the magnetic bubbles are created at the outer edge of the very far edge of the solar system where Voyager passed through, and that's where most of the cosmic rays are. But like supposedly 10% come through,
Yeah,
and yeah. So I was wondering, our because of our large iron core, molten core that we got from Thea, is that actually enough to there's always cosmic
You
rays
guys
that
still
come
can't
through,
catch
right?
me. I'm too fast for your old ass.
Isn't there always cosmic rays that always make it through that we just
the
cannot
the
stop?
higher energy ones, the Earth, the one thing about the Earth's magnetic field is it creates kind of a shield around us,
Right.
so it makes it harder to get in. But definitely cosmic rays do make it, the more energetic ones do make it their ways down.
Yeah, and then just to confirm, the largest sun type of sun that we've ever encountered was one that would ever it's like the diameter of it goes all the way past Jupiter. I mean,
Right.
the largest suns out there, right?
Yeah.
Largest stars.
Yeah, there's some that are very, very, very big. Yes,
Like go past Jupiter, right?
I believe
just
so.
about.
Yes,
That's freaking amazing.
yeah,
Because the imagine the solar wind on that thing. I mean, it's the solar system must be gigantic. So I don't know what were they found those stars inside?
Bro, it's a federal offense to look that ugly.
Look, did they find those stars inside our galaxy, or
yeah,
obviously?
Yeah,
they did. Okay.
yeah. I mean, you have like the all sorts, like usually the bigger the star, the hotter it is, the shorter its lifetime,
Right,
and so forth. And the Earth's, the sun is actually, when it gets near its its midlife, but when it dies, we're going to be enveloped by the Earth, by the sun's atmosphere. It'll bloat and go
Right.
past the and basically envelop the Earth. And these bigger stars, I mean, I don't have the numbers across, but they can be quite big and massive.
When it becomes a white dwarf, will it actually still give solar wind out? But very low intensity, right?
Probably not, because
Oh, really? Okay.
It's
the white dwarf is around 12 miles in diameter, right?
Right.
Yeah.
They're basically actually roughly the size of Earth, if I remember right.
Yeah.
So it's been a while since I taught astronomy, so.
So that nebula that's created, some of the more popular nebulas that Hubble has that is all blown out after the red giant, and then I guess the magnetic, there wouldn't be any magnetic blasting anymore. I mean,
No, no, it's after the stars go like supernova or nova. It's then they go through a different stage, and and
well, our star I thought wouldn't go supernova. It would
it won't go supernova. But
Yeah.
we're talking about the different stars. Our star though will bloat, and and then finally it'll get to the point where what it does is burn hydrogen and helium, then helium into like other elements, and then other elements, and that until it reaches the iron stage, and then it doesn't give
Right.
up, and then it collapses. Okay.
All right. One final thing, that the spacecraft that we sent out that had to have 10,000 things go exactly perfect when it opened up and blocking.
The James Webb.
Right. That's the one.
Yeah.
That is specifically related to your field. Or we're studying. It's not. Oh wait, no, it's not studying the sun. It's studying exoplanets. Okay,
Well,
it's blocking
actually
the sun. Okay.
It's actually trying to study it looks in the infrared. It's in orbit beyond the moon. It looks at the sun, and it looks at the universe rather in infrared.
Right.
And there's a new image that came out showing that they've been able to focus it. I actually saw the telescope before it was left Goddard, and they actually all around it are galaxies. It's really cool. There's galaxies all around it.
Yeah, man. Well, excellent talk. Thank you very much.
Yeah.
Okay, thank you, Gary. Other questions, comments? Please raise your hand.
Pause.
Okay. I don't see any other questions, or at least let me check the chat line one more time. Okay. I guess, thank you very much, Dr. Arge. We very much appreciate your presentation. I think it was an excellent presentation. Sorry about all these interruptions. We need to find a way to maybe block these guys more effectively. But we really appreciate your putting together the presentation and delivering it.
Well, thank you for the invitation, and it's been a real pleasure. And it's I still, like I said, it's still warm feelings for the Denver Astronomical Society. So
yeah, I had actually a couple of comments here that show interest to join your intern program. So they may actually contact you in the near future.
Yeah, and just understand that you don't have to do solar physics to be an intern. You could do planetary science, you could do astrophysics, you can do engineering. There are lots of opportunities. So I would prefer solar, but the thing with it is there's a lot you can, if you like to build instruments and have that opportunity. It's a great opportunity to come, and you get paid, and you get to basically learn what scientists do, and do real research.
So thank you very much. We very much appreciate your presentation this evening.
Okay.
Good old F. Jack Eastman here. I thought you mentioned my name, and I'm still here, and I'm still kicking and squeaking.
Yeah, I remember you from we actually, you took a bunch of us out observing one time up in the mountains to some like old army camp or whatever, and spent the weekend. It was fond memories. You're educating us and so forth. So thank you very much for that.
Well, thank you for an excellent presentation.
No problem.
Okay, I'm gonna stop the live streaming now.